I need you guys to find lesson 8 on solubility and the properties of water in your notes package. We'll be going over two things primarily today. The solubility stuff is probably going to be familiar. Okay, you talked about solubility in junior high science. I can't remember if it's 8 or 9 now, but you talked about it. Okay, and so a lot of the terms that we go over, and it's mostly terminology, okay, will be familiar. The one thing that's new in solubility is using the solubility chart that is on the back of your periodic table. Okay, it's a chart that helps us to predict whether an ionic compound, or how soluble an ionic compound is in water. Okay, it's pretty easy to use, but we will be going over that today. The second thing that we're going over, or second topic we're going over, is the polar nature of water. Okay, if you recall, last week I was telling you how if there's a rule in chemistry, water's usually the exception. Okay, and today we're going to find out why. Okay, water, like some other compounds, has a structural characteristic to it that makes it behave a little bit differently. Okay, and in fact is what makes a lot of life on Earth possible, or life has evolved around it. Okay, one or the other. Okay, so we'll be looking at that as well. Okay, questions so far? So, as we know, some substances dissolve easily, some don't. You saw that in the lab yesterday. Okay, there were some things that you added the water, and poof, they were gone. Okay, and other things you had to stir like crazy, and then they eventually kind of shrank and were gone. And other things that didn't matter how much you stirred, it wasn't going anywhere. Okay, and that's solubility, the degree to which something will dissolve in something else, not always water. Okay, is solubility. Okay, so and I mean that when I say that, it's not always water. Okay, for example, we call water the universal solvent. I don't know why, it doesn't dissolve everything, okay, but that's what we call it. Okay? If you, let's say, paint something with oil-based stain, like your fence or your deck or something like that, okay, can you get that off with soap and water if you get it on your hands? You can't. It's not soluble in water. What do you use to get it off? Oh, I mean, you still have paint on your hands then. Use paint thinner, bar salt. I wouldn't recommend this, but they'll work. Gasoline or diesel fuel will also take it off. Okay, that kind of oil-based paint isn't soluble in water, because obviously oils aren't soluble in water. Okay, but they are soluble in other oily-like substances, like gasoline and paint thinner and things like that. Okay, now the reason I don't recommend washing your hands with gasoline is, well, gasoline is flammable. Okay, and you wouldn't want that to flash on your hands. Okay, but it will dissolve. Does that sort of make sense? So some things are soluble in other things, even if they're not soluble in water. And we use that to our advantage a bit. Okay? So a substance is said to be insoluble if it will not dissolve in another substance. Okay? So insoluble means it won't dissolve, which is one of those weird things in the English language, right? Inflammable means flammable. Yeah. Insoluble means it doesn't. Okay, just know that if it's insoluble, it's not going to dissolve. Okay, if a substance remains insoluble in a solid form, it's called a precipitate. Okay, we're going to do some reactions when we do our reactions lab that will actually produce precipitates from two clear solutions. So we'll mix two things together and we'll get a solid. Okay, out of it. Okay, that solid will fall out of the solution like snow from the sky, hence precipitate. Falls out of the solution like precipitation falls out of the sky, hence the name. Okay? All right, so that's going to be an important term to know. Okay, precipitate, insoluble. Okay, those are important terms. Okay, so what you're seeing in the picture on the right is a precipitate that has formed and is in the process of falling out of solution. All right, so this is just terminology, okay? It's hopefully familiar to you. It's in your notes, okay? So you don't necessarily have to write it down. A solution is any mixture that contains a solute, that's the thing being dissolved, in a solvent, that's the thing doing the dissolving. Okay? It is also known as a homogeneous mixture. Okay? We use lots of things every day that are referred to as homogenized. Okay? Milk is homogenized. Peanut butter, if it's not the organic stuff, is homogenized. Okay? That means it all stays as one part. Okay? If you buy like the organic peanut butter or like almond butter or any of those other kinds of nut butters, you have to stir them every time you use them because all the stuff settles out and the oil rises to the top because they're not homogenized. Okay? They will leave each other, okay, in order to create these two separate things. Right? It's the same with raw milk. Okay? If you ever get milk right from the cow and you leave it, it separates. The cream rises to the top. Okay? We have it go through a process of pasteurization and such that homogenizes it and keeps the cream in suspension, okay, so that it's all one visible part, and you don't have to shake it every time you want to drink it. Okay? That sort of makes sense? Okay? So homogenized or homogeneous means one visible part. That's actually what the prefix homo means. Homo means one. Okay? Does that sort of make sense? Okay? Hetero means two or more. It actually means many. Okay? So if I have a heterogeneous mixture, that means it has two or more visible parts. Okay? So if I have a heterogeneous mixture, that's two substances mixed together that do not dissolve. It is also sometimes called a mechanical mixture. Okay? You can get it suspended, but it won't stay there. It would be like, if you've ever gone to like Subway and got a sandwich made, you know, and they say, do you want salt and pepper? And they bring out one shaker. Okay, it has both in it. Okay, it's a mechanical mixture. They're not dissolved in each other. It's not a magical salt pepper like combination. It's just a mixture of salt and pepper. Okay, you could easily separate them by just pouring water in. The salt would dissolve and the pepper would float to the top, and you'd have them separated. So a mechanical mixture, you can always separate the things fairly easily. If I poured a bunch of iron filings in sand and mixed them up, could I separate them? Totally. I just stick a magnet in there, stir it around, and all the filings would stick to the magnet, and the sand would be separated from the filings again. Okay? So there'd be some easy way to separate a heterogeneous or mechanical mixture. All right? Making sense there? What's the only way to separate the parts of a homogeneous mixture? Let's say dissolve salt and water, let's say. Yeah, I'd have to use one of their physical properties, okay, to separate them. In fact, I'd probably have to change the state of the solvent, okay, in this case water, boil it off, and I'd be left with the salts. The salts don't go with it, right? That's important to know. Never leave a boiling pot on the stove. If it boils all the water away, it will burn all the minerals that were in the water onto the bottom of the pan. It stinks really bad and it's really hard to get off. Okay, so all those minerals, they don't go with the water when it evaporates. You can separate them that way. Okay, everybody good with that? So one on the left, sorry, is homogeneous or heterogeneous?
Homogeneous.
Homogeneous, and this is
Heterogeneous.
Okay, all right. So more definitions here. Solute is the substance that is being dissolved. So if I put sugar in coffee, okay, sugar's the solute, coffee's the solvent. Okay, the solvent is any substance that will dissolve another substance. So salt, if you have salt and water, water is the solvent because it dissolves the salt. Okay, it's also why we call lots of our cleaning solutions solvents. Okay, like Pine Sol or Mr. Clean or CLR or any of those kind of things are solvents. They help to dissolve the crud that builds up, you know, on a sink or a bathtub or a shower. Okay. All right. Questions on those terms? Okay. Those are easy, like quiz and multiple choice question on a unit exam kind of materials. Okay, knowing those terms. All right, so a precipitate then, okay, because we said that was going to be an important term, is any solid produced in a reaction and will not dissolve in the solution. Okay, and I'm going to show you that like the world's weirdest video, okay, on the production of a precipitate. It's not that the video itself is weird. There's this weird, like, I don't know if it's Spanish or Italian guitar music playing in the background. It's totally out of place with the video. It sounds like, you know, some like mournful lost love kind of thing, but it goes with this video on dissolving and not dissolving. It's really strange. Okay, so we'll watch that real quick, and you can kind of see what it looks like. But I gotta stop recording because YouTube does. Okay, now, solubility, okay, is the degree to which a substance will dissolve in another substance. That is, how much solute can go into solution before the solvent becomes saturated. Okay? If something is saturated, it can hold no more. Okay, so if you go out in the rain, okay, and it's pouring rain, pretty soon your clothes become saturated. You're dripping wet because your clothes can't absorb any more water. Okay, well, a solution can become that way too. If I just have a beaker full of water and I just keep adding salt, eventually it's going to come to the point where it doesn't matter how much I stir, the salt's going to start to collect at the bottom. Or if you ever make like Kool-Aid or anything where you mix drink crystals with water to make something, there comes that sweet spot where it's just starting to collect on the bottom, and you know you've created that super sweet saturated solution, okay, that is going to be awesome. Okay, when I used to make Kool-Aid, I would actually use warm water to dissolve it, so it would dissolve more, and then I would put it in the fridge, and I knew I had it right if after it got cold there was a little layer of sugar on the bottom, because then I knew it was totally saturated and really, really sweet. Okay. And then my metabolism slowed down, and I couldn't have that much sugar anymore. It'll happen to you. Okay, now, some things obviously are soluble, some things are not. Some things should be soluble. Some things should not. Like a Twinkie. And people like Twinkies. Okay? Not as many as used to. The modern Twinkie is very different from the original cake-like dessert that it came out as. Okay? In order to preserve shelf life, lots of the ingredients of the original Twinkie have been substituted for, well, artificial things that last longer on the shelf. Okay? The original Twinkie, when it came out, was made of things like eggs and milk and flour and butter. Okay? Well, it tastes really good, but it only lasts a few days before it's no good anymore. Okay? Well, that hurts your profit margin if you're Hostess, okay? The company that makes Twinkies. So they started looking at ways to make the shelf life longer. So they started substituting some things. Okay? Obviously, milk is one of the things that causes it to go bad quickly. Butter as well, they're both dairy products. They sour. Okay? So they substituted like lactose, which is a sugar that's typically in milk, okay, and other kind of like artificial or what they call modified milk ingredients. You see that usually on the label. Okay, basically it just means it's not milk. It tastes like it, but it isn't. It gives it the same texture, but it's not milk, and it lasts for weeks on the shelf. Okay, eggs. They use like artificial protein albumin instead of eggs. Okay, problem with artificial protein albumin is it's gray. What color are eggs? Yellow. Why do you think a Twinkie is yellow? It's got eggs in it. Or because it used to have eggs in it. Now they use this protein albumin, but if they don't add anything else, the Twinkie is the same color as drywall. It's not as appetizing when it's not the golden yellow little cake. So they add yellow dye number 5. Yellow dye number 5 is banned in a lot of countries worldwide. It's a known carcinogen since it causes cancer. Now, everything in moderation. If you have a dozen Twinkies a day, the amount of yellow dye number 5 in a Twinkie will be a problem for you. If you have one Twinkie a year, it's not a big deal. Okay? So, butter, is that soluble in water? If I drop a stick of butter in a glass of water, does it dissolve? No. Okay. Lard, same thing? Lard would have been an original ingredient. Okay, those kinds of things. So the original Twinkie, if you put it in a glass of water, would have been like putting a piece of cake in a glass of water. It would just swell. Okay, it would be like a sponge. Modern Twinkie, it'll almost entirely dissolve if you put it in water. Because so many of the natural ingredients have been replaced with things that are actually fairly soluble in water. Okay, now that's great if you break your jaw and you have to have it wired shut. You could drink Twinkies through a straw. Like that, like the Kraft dinner commercial, you know, where the guy puts the Kraft dinner in the blender for his buddy that's in the full face cast. Okay, you could do that with Twinkies. You could drink them through a straw. Okay, if you leave them in the water long enough. Okay, I'm not suggesting you do that because I'm sure the texture would be awful. But okay, some things are soluble and some things aren't. Some things should be, some things shouldn't be. I'm going to file Twinkies under shouldn't be. Okay, but we do that because it extends the shelf life. The shelf life of the modern Twinkie is something like 65 days. Okay, and of course we add things to them called preservatives that will keep them fresh even longer. Okay? I'm not trying to say you should eat organic or anything like that because I'm totally like the last person who would do that. That would be very hypocritical. But okay, just know some of the stuff we eat, we don't really think about. Maybe ignorance is bliss. All right, on the back of your periodic table, you will see this chart, the solubility of some common ionic compounds in water. Okay? This is the thing we have to learn how to use, and it's pretty easy. Okay? Along the top of the chart, so the top row of the chart, there's lists of negatively charged ions. Okay, things like, well actually there's one positively charged one. There's ammonium here, nitrate, chlorate, acetate, fluorine, chlorine, bromine, iodine, sulfate, carbonate, phosphate, sulfate, okay, all those kinds of things, they're all up there, okay? The next row, okay, so the second row tells us the things that are soluble, okay? So in this row, you'll see words like most, and you'll see group 1 ions, you'll see a few things listed specifically. These would be the positively charged things that would be soluble with these things, okay? And then the bottom row are the things that are not soluble, okay? So if I have, let's say as an example, like I've got, let's say, copper sulfate. Actually, sorry, copper sulfate's on there. Let's go with silver chloride. Okay, so let's say I've got a silver chloride and I put it in water and I want to know if it's going to dissolve or not. What I do is I go up here and I find chloride. Okay, it's right here. If I go down one row, it says it's soluble with most things, which is like the least helpful thing it could say. Okay, and then I have to go down to the next row. It's not soluble if it's with copper or silver. Okay, so silver chloride would be not soluble in water. Okay, everyone follow how I did that? Okay, so I look for my negatively charged part of the compound, and then I find out where the positively charged part is. If it's in this first part, it's soluble. If it's in the second row, it's not soluble. Or sorry, third row, it's not soluble. Second row is soluble, third row not soluble. Okay, so let's try. Let's go with barium chloride. Okay, so if I had barium chloride, that would be BaCl2. Okay, would that be soluble or not? All right, so I look up. Here's chlorine again. Okay, it says it's soluble with most things, but it's not soluble with copper, silver, mercury, lead, or tantalum. The TL. It's hard to read on mine here. Okay, so since barium's not in here, barium must be part of most, and this would be soluble in water. Okay? Remember how that works? Okay. Those 8. Write them down and write beside them S for soluble, NS for not soluble. And then we'll go through them together here in a minute. So for our first one, we got calcium sulfate. So I start by looking for sulfate. Okay, sulfate's right here. It says it's soluble with most things. If it says most, then I have to go down to the next row, and I see that calcium is there. So is this soluble or not? Not. Okay, this is not soluble. Okay, potassium hydroxide. So I find hydroxide, it's right here. It says it's soluble with group 1 ions. Which group is potassium in? It's in group 1, yeah, right here, right? So these numbers here at the top of your periodic table are the group numbers, okay? So group number 1 is anything in this first column. Potassium is included in that. That one is soluble. Okay, lead 2 chloride. So here's chlorine, soluble with most things, but not copper, silver, or mercury 2 plus, or lead 2 plus. So this stuff would be not soluble. All right, tin 4 fluoride. Okay, here's fluorine, soluble with most, but not with lithium, magnesium, calcium, strontium, barium, iron, mercury, or lead. So that one is soluble. Okay, copper 2 sulfate. So sulfates again right here, soluble with most things, but not with calcium, strontium, barium, silver, mercury, lead, or radium. So that's soluble, which hopefully you saw yesterday. Okay, as it was one of your unknowns. It should have dissolved in water. Okay, number 6, potassium bromide. So bromine is right here, soluble with most things, okay, but not with copper, silver, mercury, lead, or tantalum, so that one is soluble. All right, silver fluoride, so fluorine's right here, and silver's not listed in the second row, so that stuff would be soluble. Okay, and beryllium nitrate. Well, nitrates are almost all soluble. Okay, so if you see something with nitrate and it's not one of these ridiculous looking things, it's soluble. Nitrates are just super soluble. Okay, so there we go. Make sense how to do that? That's going to be important when we start talking about reactions, okay, because we need to be able to predict whether our products are soluble in a reaction. Okay, it's just a matter of, okay, here are my products, and I go to my chart and see if they're soluble. All right, could that be something I ask you to use in a quiz? Like on Tuesday? Yeah, definitely. Okay. All right, questions on that? All right, so let's take about a 3-minute break here. So we'll come back at 9:32. Okay, you can answer any messages you got to answer there, and then we'll get started on the polar nature of water. All right, so let's pick up here. So we're going to talk about the behavior of water and the structure of water and how the two are related. Okay, so we know that in an ionic compound, when there's an ionic bond, electrons are simply traded. Okay, the nonmetals take them, the metals give them away, and that's that. In a molecular compound, or a covalent bond, the electrons are shared. Okay, so they share their valence or outer electrons, which is why it's called a covalent bond. But when we say share, it gives the idea that the sharing is like sharing should be, equal, but it's not. Okay, and in some compounds, the sharing is in fact so unequal that it ends up making one end of the molecule positively charged and one end of the molecule negatively charged because the electrons hang out next to one of the elements more than the other. Okay? And that has to do with their electronegativity, okay? Which is actually one of the numbers that's in your periodic table for each element. Okay, so it's right underneath the atomic number. Okay, you'll see a number there that's labeled electronegativity. So for hydrogen, the electronegativity is 2.2, which for a metal is actually fairly high. Okay, but if we look at oxygen, its electronegativity is 3.4. Now, electronegativity is basically how tightly or how hard that element will hold on to electrons. Okay, so oxygen holds on to electrons far more tightly than does hydrogen. Okay, this is also why if you look over here with all of these nonmetals, okay, all the nonmetals have fairly high electronegativities, but if you look at the metals, they're all tiny numbers. Okay, quite a bit smaller. That's why ionic compounds work the way they do. Okay, the electrons just go to the electronegative nonmetals. But when it's two nonmetals together, okay, they have to share better because they're both electronegative. But when we're talking about water in particular, hydrogen is not nearly as electronegative as oxygen. So the electrons spend more time down here around the oxygen than they do around the hydrogen. So normally, a hydrogen atom would have its electron going around in this orbit. Okay? Once it gets into a molecule, makes a water molecule with oxygen and another hydrogen, that orbit changes. And this electron starts doing this. And kind of just barely, doesn't even really get around the proton, kind of does this instead. So it kind of hangs out around the hydrogen atom, but doesn't go past it. And so what it ends up happening with the water molecule is there's two protons sticking out the top, okay, with no electron, because the electron actually ends up below it more of the time. So you get a water molecule that's got two positive charges up top and two negative charges near the bottom, meaning it has positive poles and negative poles, hence polar molecule. Okay? So a polar molecule has charged ends. It's still electrically neutral. It has the right number of protons and electrons, but the electrons aren't distributed in a way that makes it look that way. Okay? Now, if I've got a water molecule here, okay, so it looks like Mickey Mouse, okay, and this end is positive, and I've got another water molecule here, what could happen between the negative end of this water molecule and the positive end of this one? Yeah, exactly. They'll attract each other. Okay? Opposites attract. So these two things will attract each other, and they'll actually form what's called a hydrogen bond. Okay? Hydrogen bonds are weak. They break, but they reform very, very easily because they're based on this attraction between the water molecules. You've seen this lots of times in your life. Okay? You know when you fill a glass and you're getting like right near the top, and if you just are careful, you can actually fill it slightly more than full, right? So if this is your glass, you can actually make the water kind of do this. Okay? That's because water is polar, and the surface tension is because of these hydrogen bonds. Okay? Do you break that? Can you break that surface tension real easy? Yeah, like even if you touch it, it's gonna go. Okay? You'll break those hydrogen bonds. They'll reform, but they'll break. Okay? Similarly, if this glass and the water in it is really, really cold, water will start to condense on the outside. But those droplets will actually stick to the glass until they get so big that the hydrogen bonds are no longer strong enough to stick them to the glass, and then they'll run down the side. Okay? Those are all places where in your life you've seen evidence of water being a polar molecule. Okay, and these hydrogen bonds forming as a result. Okay? So what we need to know about hydrogen bonds is this. The sharing of electrons is not equal. Because the sharing's not equal, ends of the molecule can become positively charged and negatively charged. Okay? That's the nature of a polar molecule. Every semester, I put a question on the unit exam about water being a polar molecule, where I ask you to explain this very thing. Okay? So, something is a polar molecule if the electrons are not shared equally, opposite ends of the molecule can become positively or negatively charged and form hydrogen bonds with other polar molecules. Okay, that's the nature of a polar molecule. That's the part you have to be able to explain to me. All right, so covalent bonds in which the electrons are not shared equally, okay, are called polar covalent bonds. So this diagram is showing in a much clearer and better way than what I drew, okay, these hydrogen bonds between water molecules. So the hydrogen atoms on a water molecule are going to be attracted to the negative end of another water molecule, and they'll bond to it, okay? In fact, a water molecule has 4 bonding positions for other polar molecules, the 2 hydrogens and the 2 sides of the oxygen atom at the bottom. Okay, so you can see that again here in the picture on the left. Okay, so the water molecule is shaped almost at a 90-degree angle. Okay, and so it's separating those charges by as much as possible. Okay, it's separating the positive charges by as much as possible. It's separating the negative charges by as much as possible. Okay, and so it gets that shape because of that. Okay. Ever freeze a water bottle? What happens to it? Yeah, right? It'll sit just fine when the water's a liquid, but as soon as you put it in the freezer, the bottom puffs out. Okay? Why? Because water gets bigger when it changes from liquid to solid. Very few compounds or elements or any other materials, period, do that. Okay? Water does it. It's one of those things, right? The natural rule is, as things get colder, they contract. And everything obeys that, except water. Okay? The reason that water expands when it freezes is because it's polar. So it's got these polar bonds, okay, that are there, and they're these hydrogen bonds that are holding them together. The problem is that once you get water too close to itself, it starts to repel, because those negative oxygen atoms start to get too close to each other, the positive hydrogen atoms start to get too close to each other, and at about 4 degrees Celsius, that's where water is smallest. You start contracting it any further, and repulsion starts to happen. Okay? And right as it freezes, the repulsion hits its maximum, and the water molecules jump apart and then change to solid. Okay? And so ice takes up more space than liquid water. Okay? It expands outwards. If you have a sealed container, it can break it, okay, when it freezes, okay, things like that. All right? It's also why, I don't know if you ever noticed this, but ice floats. Okay? If something's going to float on something else, it's because it's less, starts with D. Dense. Yeah. Okay? Well, ice looks like this. Liquid water looks like this. Ice is clearly less dense than liquid water. Okay? Thus it floats on itself. That's exceptional. Most things, if you have the solid and the liquid together and you plop the solid in the liquid, it sinks right to the bottom. Okay? So if I had like some mercury at room temperature and I took some frozen mercury at like minus 45 and I dropped it in there, it would sink right to the bottom. Okay? Just about everything else, okay, in its solid form is more dense than in its liquid form. Water's an exception. And this is important. If it wasn't, life on Earth would be a lot different. Think about what happens in the wintertime. Okay? Around here, the lakes all freeze, right? if ice was more dense than liquid water, the lakes would freeze from the bottom up, and then they would freeze solid. But they don't freeze solid because the ice is less dense, and so it forms on the top. And then because it's less dense, forms an insulating layer against the cold air, and there's liquid water underneath. Okay? I mean, nothing would survive in a lake through winter if water was more dense in its solid form than its liquid form. Okay? Kind of important. Okay? Also, if you get out in a rainstorm and you get wet, okay, you're going to get cold pretty quickly. But if you can pile snow up on yourself, can it keep you warm? Anybody ever build a quinzhee? Or you make a pile of snow and then you hollow it out? Okay, snow's a good insulator because it's full of air spaces. It's less dense than liquid water. Okay, it can act as an insulator. Liquid water is a terrible insulator. Okay, but water as a solid is an excellent insulator. Okay. All right, making sense? Okay, so these are all caused by water being a polar molecule. These things that we're familiar with water doing are exceptional. Okay, it's not the norm, okay? And it's because it's polar. Okay, trees use this to transport water. Okay, when you think about if you've ever seen like the giant trees out in BC, the big sequoias and things like that, they can be over 100 meters, sometimes several hundred meters tall. And they've got to transport water from the ground to the top of the tree. They do that with no expenditure of energy. Okay? If you or I wanted to move water 100 meters up in the air, it would take a lot of energy. Okay, because we have to fill a bucket and carry it. Okay, it would take a lot of energy. Plants move buckets worth of water up to the top of themselves every day and use no energy to do it. All they do is harness the polar nature of water. Okay? So inside the tubes, inside the tree, okay, the ones that transport water, okay, the water moves up. It moves up because as water evaporates from the leaves, it's hydrogen bonded to the water molecules that are still inside the leaf. So when that water evaporates, it pulls on the water molecule below, which is hydrogen bonded to the one below that, which is hydrogen bonded, and so on. It's like a barrel of monkeys. You ever play with that as a kid? Right, where you can hook the arms and legs together? Okay, that's what it's like. So when you pull on the top one, it pulls all the others. Okay, and so when that one water molecule evaporates, it creates a pulling action on all the ones below it because they're hydrogen bonded together. Now, these tubes are microscopic. Okay? We're not talking about like a straw. Okay, you can't do that in a straw. Okay, but you could do it in a microscopic tube. We're talking about small amounts of water in each tube, but it adds up to a lot. Okay? And so it can support and pull on this column of water. So there's two types of hydrogen bonding that are going on here, and these two terms are going to be important. There's cohesion. Okay, so cohesion is right here, and it's water molecule bonded to water molecule. Okay, co meaning like the same, cooperate. Okay, and then there's adhesion, where the water can hydrogen bond to the cell wall of the tube. Okay, so back to the barrel of monkeys analogy. Okay, you've got all the monkeys attached to each other, but they've also got another free arm that can grip the inside of the tube and keep them from falling. Okay. So no energy required. It's just using the fact that water is polar to be able to haul it up the tree. Okay. So there's an example of a living organism that has evolved around the polar nature of water. Anybody ever skip a rock? Okay. Is that because of hydrogen bonding? Surface tension, right? You're bouncing the rock off the surface tension of the water. The key to skipping a rock is angle of entry, right? If you just chuck the rock up in the air and it comes down like this, it's just going to break the surface tension and fall in. But if you can get it to hit at an angle, that surface tension, those hydrogen bonds are strong enough that it'll bounce right off of them. Okay, maybe several times if you've got a really good throw and a really flat rock. Okay, again, key, angle, and the rock has to be flat, smooth. Okay? If it's like all jagged and you try and skip a jagged rock, you might be able to get it to go once, but probably not. Okay? Flat rock, thrown at a low angle, okay, is gonna ride that surface tension. Bugs do this all the time. You ever see bugs and this looks like they're just floating on the water? Okay? They're actually doing just that. They're riding the surface tension. They're not big enough to break the surface tension so they can sit right on top of the water, okay, without sinking. The Jesus lizard, okay, or that one that can run across, okay, kind of a similar thing. If they keep moving their feet fast enough, I mean, they're breaking the surface tension, but it breaks late enough that they're already on to the next step. Okay? Now, they can't run across a lake, but they can run across, you know, a small bit of water and evade a predator, same thing. Okay, other examples of surface tension. I had one afternoon where I tried this for like an hour and a half. It's an hour and a half of my life I'll never get back. And I wasn't able to do it. Okay? But apparently you can lower a paper clip onto the meniscus, the surface tension of a glass of water, and have it sit there. Okay? If you've ever seen dew sitting on the leaf of a plant, okay, that's because of hydrogen bonding. Okay, the wax is a polar molecule. The waxy cuticle of a leaf, okay, is a polar molecule, so it'll sit there and it'll adhere, not cohere, but adhere to it, okay, and stick until the wind comes or whatever, okay, and then it'll fall to the ground. Okay, so we've got adhesion and we've got cohesion. So I think we had cohesion in here, okay. So cohesion, oh, sorry, that's the wrong sentence. So cohesion, we're just going to write is water to water. So cohesion is water to water, and adhesion is water to something else, like the side of the glass, the surface of a leaf, the inside of the tubes in a plant. Okay, and then adhesion, okay, is the clinging of one substance to another. So that would be water to something else. Okay, so that's what I was talking about. Sometimes you can have bugs that sit on the surface, or the Jesus lizard that can just run across. Okay, all due to that same idea that those hydrogen bonds, they're weak, but they're strong enough to do some things. Okay, that's it for today. My suggestion to you right now would be to probably get together with your group, maybe look over your data, and maybe start talking about the analysis a little bit. See if you can figure out what some of those unknown compounds might be in your last 5 or 6 minutes of class here. Okay, I want to give you some more time.